So this is the first paper that we're doing on this channel. So I hope you like the way I'm solving. And this is computer science paper 1, that is theory fundamentals. And we're looking at the new code, which is 9618. 1-2, and this is the October-November 2022 edition of this paper. So let's just start. Okay, first one. Okay, if you have any questions regarding the paper, do let me know in the comments below, and I'll try to reply as soon as I can. Okay, first one, a virus checker. This one is pretty simple. We just have to find the appropriate purpose and match it to that. So this is used to scan malicious program code, obviously. A disk formatter will initialize a disk. Backup can create copies in case original is lost. There we go. Disk repair it fixes inconsistencies in a disk, and defragmentation, it does not decrease file size. Okay, it reorganizes files so they are yep. Now, compilers and interpreters translate program written in high-level language into low-level language. State 2 drawbacks of using a compiler compared to an interpreter during program development. Okay, so why is using a compiler worse is our question. So firstly, the program won't run if there are any errors. So present. Secondly, errors cannot be corrected in real time. So another one, because why not? You could write any of these and score 2 out of 2 for this one. Any two of those. Okay, what else do we got? Okay, so if there is one error present, other false error may be reported. So third one, if an error is present. And one more, the code cannot be changed unless we recompile. So code cannot be changed unless we recompile. So you can add any two of these 4 and you can score full marks on that. Explain why high-level language programs might be partially compiled and partially interpreted. So firstly, the machine code is generated at runtime, so it's optimum for the CPU. Machine code. And secondly, the partially compiled programs can be used on different platforms as they're interpreted when run. Programs. Okay, now these 2 points are the only ones given in the MS, so make sure that is what you're writing. Cool. Next one, we have some conversions to do. So this is a 2's complement binary integer, and we have to convert it to denary. So starting with, if you want to convert 2's complement to denary, what we're going to do is just subtract 1, because remember, when we're converting a normal binary number to a 2's complement, in the end we add 1. So we're going the other way around, right? So you subtract 1. And then you're left with, this becomes a 0 and this becomes 1. So you don't do 10, but this becomes a 1. So it becomes 0, 0. Oh, I'm sorry. We change the sign because we're subtracting 1, right? 0, 1, 0, 1, 0, 0, 1. Now this is our number. Now we're yet to get the actual number, right? Because this is a 2's complement, it also means that the numbers are flipped. So next step will be to flip these digits. So 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. Oh my god. 1, 0. So this is a binary number and we have to convert it into denary. That means this is a 2, 4, 6, 8, 32 and 64. Now we just add these up and what do we get? 64 plus 32 plus 8 plus 2. That's 106. And since it's a 2's complement, it means it's a negative number. Minus 106 is your answer. Now you have to convert the binary integer into hexadecimal. First up, we split into 4s. Now this is 1, 2, 4, and 8. This is 1, 2, 4, and 8. So we have 8 plus 1. My bad, not 8. 8 plus 1. And then here we got 4 plus 2. So 9 and 6. 96 is our answer. Convert the unsigned binary digit into binary coded decimal. Show your working. So first, we can just convert this to denary. We have here, okay. Uh, 128 plus, this is 64, 32, 16, 8 plus 4 plus 1. Okay. Plus 16 plus 4 plus 1. So 149 in denary, okay? Now, we have to convert 149, these digits, into back to binary. So first we do 1. For 1, we have 0, 0. This is 1, this is 4, this is 9. 0, 0, 0, 1, right? And then we have 0, 1, 0, 0. So, yeah, that's correct. And then we have 1, 0, 0, 1. So our answer is, that's a final answer. Okay, now I have to add this. Let's add it. 0 plus 0 is 0. That gives us a 1. 1, 1. 1 carries over 0. 1 carries over 0. And we got 1, 0, 1, 1. That should be good. Okay, we're done with the second question as well. I love logic gates. I think it's very fun to do them. A greenhouse gas has an automatic window. The window X operates according to the following criteria: temperature, wind speed, rain. Too high, okay. Cool. The window X opens if the temperature is too high and wind speed is acceptable and the rain is not detected or manual override is off. Cool. So firstly, let's see. We have to get the temperature has to be too high, right? So it has to be, okay, it's a positive for temperature. Let's see. And the wind speed has to be acceptable. So wind speed acceptable is a negative. So I just go by 1 as a positive and 0 as a negative. That's how I like to say it. So we want the wind speed to be high. to be acceptable, right? Which means we need a positive gate over there. To make it a positive, we're going to do the NOT gate. So, first one, temperature. Oh my god, I'm so sorry about that. This is an AND gate right here. Starting with an AND gate between temperature. Now, we need this to turn to a positive, right? So first we're going to add a NOT W gate here and put it to an AND. Secondly, the rain should not be detected. Now rain has to not be detected. So this is a, or the manual ride is off. Okay. I'm doing this for the first time too, so which is why I'm a little slow at this. This has to be off. Okay. It's an OR gate here, so we know for a fact that this becomes a OR gate, right? Like that. And because we want, these are all negatives here, we need to use a NOT gate to convert that. See, only then will we get a positive value to go through the... What happens is, see, when it is off, which means here you get the value of 0. After it goes through the NOT gate, it becomes a 1, right? And this becomes a 1, which means if either of these are present, it is going to go through the OR gate, right, as a positive value. So that's that. Alright, and these have to be joined by this AND in the middle. So we're going to do just that. This is our AND gate. And then, yeah, that's it. Draw it in a better way, use a scale to look better. Okay, this is the next bit of the question. Complete the truth table for the logic expression not A or B or C and B nor C. Sorry, it's just like working this one out. I'm just gonna erase that. Start from scratch. Okay. Firstly, let's check for A or B or C. In the first case, A or B or C is not true. So not of not true becomes true. So that is 1. And B nor C is also true for this one. One sec. Yep. So B nor C is also true for this one, which means A 1 and 1 and gate in the middle, which means X is also true. A or B or C here is true, and we want not of true, so that becomes false. And B nor C, that is also false. So that becomes A0 here. Okay. Then we have A or B or C, that is false. Sorry, that this is true for this one. A or B or C is true, so not of true becomes false. Oh my god. False, and B nor C is also false. This is also false. Okay. Next up, A or B or C is false and is true, so not of true becomes false. That's correct. And B nor C is also B nor C is also false, so this is also false. Same goes for this. See, it's a simple thing here. Since we want this to be a 1, because it's an AND gate, which means both of these have to be true. If we want this one to be true, it means we need to get neither of these. And in all of these, right, we have one, like from here to here, either A is true or B is true or C is true, which means this AND is never going to satisfy. But just for the sake of it, I will work it out. But in the end, it won't satisfy anyway. Okay, B nor C is true for this, but it's an AND in the middle, so it goes to a 0. Now, this again, A is there, so this becomes a 0 since it's a NOT. and this is also 0, so that's a 0. So 0 and 0, 0. Alright, this is a 0 and 0, so 0 again. So only one case where we get a true value for x, so that's that. Okay, next one. Embedded systems contain read-only memory and random access memory. Explain the reasons why ROM is used in an embedded system. Okay, firstly, it stores the data, that doesn't change. Yep. Second, it stores data when the device is there's no power connected to the device, right? So power, so that should give you 2 marks. But this also stores the boot up instructions, so this could also be an alternative. Well, it can also store system software, so yeah, that could be a, you can just write that here. Cool, so those are 3 points. You can write any 2 to get 2 marks. You may not want to write these 2 as 2 separate points because they are not allotting marks like that. So yeah, these should be the 3 separate points if you want to get 2 marks. Well, you can write any 2 and get 2 marks. Okay, state a difference between data verification and data validation. So data verification is checking if the input data is the same as the original, and data validation is checking if it is the data entered is like sensible or is the correct data type. So yeah, data validation is checking if it is sensible, so type, etc. Sorry, validation. Okay. A checksum can be used to detect errors during data transmission. Describe how it is used. Okay. So first one, the checksum value is calculated before the transmission of data. So before it's calculated, then this value is also transmitted with the data. Okay, so the computer that receives it will recalculate the check sum, right? So it will recalculate this sum. So what the whole idea of this is, suppose you have this value, right? So they check the sum of this, right? And that is stored as the value, this checksum value, right? And then it's transmitted to your computer. Now this computer, suppose, gets an error and instead it has this value. Wait. So it's that. Now you just see the number of ones here and the ones here are different. So the value of the sum will be different, and so it will know that there has been an error. So first, the sum is calculated here. Then the sum is also transmitted to the receiving computer. Then the computer will calculate the sum again to check. So receiving okay, and then the last point is that if it is matched, then there is no error. If it is not matched, error has occurred. If values okay, next one. One validation method is a presence check. Describe two other validation methods that can be used to validate non-numeric data. Alright, so make sure you're writing for non-numeric. First one is check type. Now, in the MS, they've not just given it for like the names of it, so you should write down what you mean. So check type is data in required format. Right? So if you're expecting a character, it cannot be an integer, basically. Then next one, you can check the number of characters. So suppose if in a college system you have a student login or something like that, and which is just like 5 characters of your name and surname combined. So if someone tries to enter 6, it'll show an error. Just that. And since they're talking about non-numeric data, right, which means there is no number present, so you can just say that ensure no numbers are present. Okay, that's cool. So we're gonna start with question number 5. The relational database garden has the following tables. So we have table owner and table tree. The database is not in third normal form. Explain how the database can be normalized through 3NF. Okay, so one issue here is this is a many-to-many relationship, right? And for it to be in 3NF, we have to remove this. So your first point is remove the many-to-many relationship. Right? Now how we can do that is, alright, now what happens here is this tree ID is the primary key here, right? And we have 2 tables here. So since each owner can have multiple trees, right? So we can kind of this is how we represent many to many, right? It's basically each owner can have multiple trees, and each tree, well, not each tree exactly, but so since it's just a tree, so they're not talking about a specific tree, but they're talking about a type of tree, right? Because we have scientific name, max height, and fast growing. Each tree will also have multiple owners, right? So it is a many-to-many relationship. So what we're going to do is we're going to create a new table, right? and we're going to take out the tree ID and tree position, because this tree position is what makes the tree unique, right? So we're going to take we're going to make a new table, create new table with okay, so in the new table we need columns. So we're going to keep this owner ID because that's how we will identify a tree, right? So with tree ID, owner ID, and tree position. Now the table has these 3 columns, right? And what happens is this table creates a link between these two, right? So suppose this is our owner table. This is a tree table. Now let's say this is let's make a new one, specific tree table. Now each owner will have only one of a specific tree, right? So yeah, because it will have a different tree ID, so it will be a 1-to-1 relationship, and each specific tree will only have one connection to tree ID, which will have the scientific name and everything, right? So instead of having this, we will now have this, which is in the third normal form. So this table will link owner and tree, right? So this is our link. Now what we can do is, in this table we have these 3, right? We can make a composite primary key. Okay, we don't need this right now. Since we cannot make either of tree ID or owner ID a primary key by itself, we can make a composite key, primary key. All right. Yeah, so that should give you a table in 3NF and 3 marks. Write a structured query language script to add a new record in table 3 to store the following data. Now our table 3 has tree ID, scientific name, max height, and fastness. Alright, so since it's in order, we can directly insert into. So we got insert into, and then we can directly just write tree and values low 1276. So we don't need to add the quotations because it's just a numerical value, and we don't need to for the boolean value either. Don't forget the semicolon. Now there's one more way you can do it is you can add tree. I'm just gonna do it for another pen, and then you could add all of the field names with commas, and then yeah, same thing. But since it's already in order and we're adding to all, we can just directly skip this part. So I'm just gonna do that. Okay. Moving on. What is meant by a candidate key? So an attribute that could be a primary key in a table but isn't. Okay, sad. Describe using an example what is meant by a data dictionary. So always remember, data dictionary stores metadata about the database. Right? It's kind of the data about data in a way. And example can be the data types. See how data types are just is just data about the data, right? So data types or primary foreign keys. It's a lot of relationships. Okay, relationships, got that one. What else? The field names. So you could just give any one of these and that should be it. Okay. Describe what is meant by a logical schema. So this one I kind of just had to look at the MS because I didn't really know what exactly they were expecting. But it's an overview of a database structure. Right? And it models the problem. Models the problem or the situation is what they say. And okay, I think we can just stick with these two, but they also say that it models the problem by using methods such as an ER diagram, and it is independent of any particular DBMS. But okay, it's an uncanny question. I don't think they usually ask such questions, but okay. A student uses network laptop computer to send an email to a colleague. Explain how a digital signature ensures the email is authentic. Okay. All right. So this is a very peculiar way of answering this. They do say it's compulsory. So what they're saying is the the digest encrypted with the digest is encrypted and it can the signature can only be decrypted with matching the sender's public key. So here's the deal. In this, the sender's private key and the sender's public key is underlined, which means you wouldn't get the mark unless you've written that. Also, the only is important. Okay. Describe how a firewall protects the data on the computer. Okay, so there are a few ways it does that. Firstly, it monitors the traffic. You can just say you can either say it monitors incoming and outgoing packets, or you can just say monitors traffic. That's good enough. Or it will so it can block transmissions that do not satisfy the criteria. Now the criteria can be anything dependent on the user and depends on the situation, but anything that doesn't meet the criteria, the firewall can block. And alright, so it can also check against a set of rules for acceptable data. Alright, so here's the deal, right? So first it will monitor. I wrote it in the wrong order, but that's fine. So it will monitor the traffic. It will check against whatever set of rule there is for acceptable data, and then if it doesn't meet that, then it can block the transmission. Okay, cool. The student records a sound file. Explain the effect of increasing the sampling rate on the accuracy of sound recording. Okay, so that's simple. When you increase the sampling rate, right, which means you increase the number of samples taken per unit time, so it will improve the accuracy of the sound file. Right, obviously. Then okay, so there's one more way. Okay, so the way that they have phrased it is the digital waveform. So the one that is being recorded is more similar to the actual analog waveform. Okay, which is just a way of saying how the accuracy is increased. And you can also write the details stored, the amount of details stored is increased. Now it's almost the same way, the same thing said in different ways, but yeah, amount of details stored increases. Alright, explain the effect of decreasing the sample resolution on the file size. Okay, so obviously when we're decreasing the sampling resolution, the file size decreases because less data to store. Yep, and we also have to write why. So because fewer bits are used to, so each sample, basically what happens is, if this is your wave, right, sampling rate is, suppose if this is 1 second, in one of the samples you take 1, 2, 3 and 4 readings, right? If in the other sample you take say 8 readings, so the second sample will be much more accurate, right? And what is sampling resolution? It is just the number of bits assigned to store each of these samples, right? So what happens when you decrease the resolution? Firstly, the file size decreases because fewer bits are used to store each sample. So we're on question number 7 now. So it's our processors and registers accumulator. Alright, so it's a trace table question, and make sure you always go back and refer to this table, because don't trust yourself too much with knowing everything. So I just have a copy on my laptop just so that I don't have to keep going back and forth, but make sure you refer to it. Alright, so LDR 0. LDR is simply direct indexing, right? Just gonna check, yeah, immediate addressing. My bad. Okay, so we start here, 75. So 0 goes into our IX. Cool. Second one, so 76, 77, 78. That's okay. LDX 110. So LDX means indexed addressing, that is whatever is in 110 goes into our accumulator. So 1 goes into our accumulator. Okay, now 77 is CMI. CMI is the address we used again. Compare the contents of accumulator with, okay, so we compare 1 with 102, so we're comparing 1 with 112, right? And next up we have JPE 91. So JPE is, okay, so if the compare was true, then we jump, right? Address to be used is at the given address. Okay, so my bad, so this is indirect. So CMI is basically you check what's in 102 and this is your address, so you go to 112 and see it's 0. So the compare, now we have 1 here and 0 here, so the compare is not true, right? Which means we will have to do for 77 we don't have to jump because it wasn't true, right? So, sorry, for 78 we don't have to jump. Now 79, compare 103. Now CMP is direct, so 103 is 4. It's not true, so nothing happens. We move on to 80. 81, add 101. So you add 1 0 to 1. So you can just write 1, it stays the same. Even if you don't write, it's fine. You can just like continuously write that or not, it's the same. 82, store 101. So store is basically store the contents of accumulator in given address. So right now it's at 1, so we will store that in 101. So this becomes 1 here, right? Alright, hold up, I think we messed up a little bit. Compare 79, 10. Okay, I see what we got wrong here. So JPN, which means that if it is false, then we jump. So after 80, we directly jump to 84, right? Which is increment the accumulator. So we just add 1 and then it becomes 2. Okay, we missed that one. So we got to be careful with that. 85, store 101. So we store 2 in the accumulator. And 86, LDD 100. So LDD is direct addressing load the contents of the location to accumulator. Okay, so 100, we got 0 here, so we just put 0 in the accumulator here. Increment the accumulator at 87, so this becomes a 1. 88 is store 100, so we store 1 in 100. Okay, then 89 is increment IX. This becomes 1 because it was at 0. We just increment that. And then 90. Now this is the first time we get to 90, right? Jump to 76. So we are jumping right here. Okay, 76. LDX 110. LDX is what? Okay, so index register plus 100. Okay, so 110 and then index register is 1, so this becomes 2 into the thing. I highly recommend, wait, my bad, one sec. I'm just gonna erase this. Okay, so I figured it out. I was thinking in the wrong direction. Again, I think I misinterpreted what LDX means in the first place, right? So I'm gonna correct that. Well, we're here now. LDX is basically, if we read this out, and form the address from address plus contents of IR. So the address that we have here is 110, and then we add 1 to it, because right now in our indexed register we have a 1. So 111, that's a 4, which is why we load a 4 into the accumulator. Now 77, we will CMI, so we will compare contents of accumulator. Okay, so first CMI 102, so we'll go here and then we'll check 112. So 0, compare that with 4, that's not equal, so it's a false. Then we have JPE, so we will not be jumping because it wasn't true. Now 78, sorry, my bad, 79. 79 is compare 103. So 103, so that's a true, right? But this is JPN, which means we wanted a false to be able to jump. So it's not. So we don't jump, we carry on and do 81. Add 101. So we add 0 to 4 and that stays a 4. Okay. Oh wait, I'm sorry. 0, 1. Oh my bad. So 101 is 2, not 0 anymore. That was, again, try to look at smaller details here. Okay, so this becomes 6. Then we have 82. In 82, we have to store whatever is in the accumulator in 101. So this becomes 6 here. 83. Jump to 86. Okay, so 83 and then we go to 86 directly. And in 86 we have LDD 100. LDD, just gonna check here. Location at the given address. Okay. So at 100 we have this 1. So we're gonna do that and load 1 and then 87. Increment, so this becomes a 2. In 88 we have store in 100. So 100 is right here, so this becomes a 2. Okay. In 89 we have increment the index register. So this becomes from 1, it becomes a 2. And 90 finally jump to 86. So we don't have to do anything. So that should give you 5 marks. You have to pay attention to everything you're doing and you can score 5 marks easily. Okay, so now we have again some instructions here and let's see. So we have memory address and the value of data. So the current contents are, show the contents of accumulator after execution of the following instruction. So XOR is just operating the XOR operation bitwise to this with this. So we're just going to compare this real quick. 0 0 0 1 1 1 1 1, and then we just bitwise compare it like this and write the XOR function. So we have firstly, okay, let's begin. So 0 and 0. XOR is basically we need it to be opposite. So 0 and 0, they're the same. So we get a 0 here and we get a 1 here and then 0 0 because 1 and 1 are also the same, and 1 1 0 0. That's the answer for that. Okay, next one. Current contents of the accumulator are this. Show the contents of accumulator after execution of AND. So first we go. This is, since there is no hashtag, this is a memory location, which is right here, which is basically 0 1 0 0 0 1 0 0 1 1 1 1 0 1, and we have to perform AND bitwise. So 0 1 0 0 0 0 0 1, and that's that. Now LSL number 3. Alright, let's check what LSL is. Bits in the accumulator are shifted logically n places to the left. The left, remember? Okay, so we move it 3 places to the left. Okay, so this one goes here, right? 1 2 3. So I'm just gonna write this block in the first 5 places, 1 0 0 1 1, and just introduce zeros to the right. Cool. Yep. Okay, now current contents are this. Show the contents of the accumulator after this or 5 1. So I'm just gonna go take a look at 5 1. Okay, so we have OR here, so that becomes 1 1 0 1 set 1. Cool, that's that. Write the register transfer notation for each of the stages of the fetch execute cycle described in the table. Okay, so copy the address of the next instruction into the memory address register. So MAR is a memory address register, and the address is being copied from okay, next instruction. So we have it stored in the PC, right? So it is being doing that. The arrow shows that the transfer is happening from the PC to MAR. Now increment of the program counter. So program counter is a PC, and PC, you just add 1. Simple as that. Copy the contents of memory data register into current instruction register. So this is CIR. So it is being transferred from the MDR to the CIR. So that's that. Okay, now we're on to the 8th question. The following bitmap image has a resolution of 4096 into that pixels and a color depth of 24 bits per pixel. The image is displayed on the monitor and has a resolution of this. Tick one box in each row to identify the effect of each action on the image file size. So it's a bitmap. Keep that in mind when we start this. All right. First up, action is change the color depth of the image to 16 bits per pixel. So first, the original is 24. I'll scroll. Okay. From 24, we're going to 16. So it will decrease the file size, obviously. Change the screen resolution to that. Okay. So changing the screen resolution will have no effect on our picture. A picture will the picture has a resolution of this. So no matter the screen resolution, the picture will remain of that resolution itself, and the file size won't change. So no change. Change the color of the rectangle from black to red. Again, no change, because you're changing the color. It will take the same number of bits to store the color, whichever color that is. So it's fine. 2 benefits of creating vector graphic instead of a bitmap. So firstly, it can be enlarged without pixelation. Sorry, spelled it wrong. And okay, so this is one. Secondly, it's usually a smaller size, file size. Another one, which is not a typical one to write, but individual components of a image can be altered. So suppose this is our image, so we can take this arrow for example. So that can individually be altered, leaving our other elements the same. So okay, can write any two of these. They've given 3. A second bitmap image is stored using a color depth of 8 bits per pixel. The file is compressed using run length encoding. The table shows compressed and uncompressed values for this part. Complete the table. The first row has been completed for you. So simple. Now this is 1 EA, so we have 1 EA, and then 2 FE, so 2 FE, and then 3 F2, same way. So all right. Sorry. Okay. So first one we have 2AB, so AB, AB. Then we have 2FF, so FF, FF. Now keep in mind this is not 11 Ds, but it's actually just 1D. So 1D and then 1, 6, 7, 6, 7. That's the answer here. For this case, you have 2, 3, 2. So because there are 2, then 1, 8, 0 and 2, 8, 1. Cool. RLE is an example of lossless compression. Explain why lossless compression is more appropriate than lossy compression for a text file. Okay. Firstly, in a loss, what's the difference between lossless and a lossy? So lossless is basically when we do RLE, the quality isn't compromised, right? The quality of the compressed image isn't compromised. And if it was lossy, we would have seen the quality to be worse. So why is it better? Firstly, no data is lost in lossless. So in lossless, no data is lost, right? And the second one, since it's a text file, okay, so when we're talking about a text file, if any data will be lost, the text itself won't make sense. So if suppose this is our sentence and the no is lost, suppose, so it becomes a lossless, data is lost, and that would make us make the whole sense to be haywire and not what it was meant to be. So if data is lost, text will not make sense. Okay. One use of AI is for facial recognition software. Describe the social impact of using facial recognition software to identify individuals in an airport. Okay, this is slightly open-ended, I'd say. So I'm just going to refer to the MS for this one because let's see what they're expecting, right? So one point is faster boarding, since you already know, since it's fed into the AI and you can just check if they're actually the people, and it makes the security checking and everything much easier. Faster boarding, you can catch criminals, sure. So these are the two simplest ones according to me, but let's see if there's more. Okay, there's one just that says individuals will feel safer. then there is one that says incorrect recognition of faces leads to mistakes such as access to facilities. I think we should just stick with these two. Usually questions from this chapter are rather like open-ended and don't have like one correct answer, so you just kind of gotta shoot your shot and hope it's correct. Let's look at question number 10. Okay, when did we get to 9? This question 9. Oh, this was question 9 in just 2 marks. Okay, 10th one. A LAN consists of 4 computers, 1 server and a switch. It uses a star topology. Complete the following diagram to show how hardware is connected. Okay, so all 4 computers need to be connected to the switch. So computer 1, computer 2, computer 3. I think you can definitely draw this much better. And then it is connected to the server. The switch is connected anyway. A router is attached to one of the devices on the LAN shown in part A to connect a LAN to the internet. Identify the device. Give reason for your choice. Okay, 1 second. Which device are we trying to identify? One of the device. Okay, so we can either talk about the server or the switch. Let's talk about the switch then. So, okay. Now, this router can be attached to the switch or it can be directly attached to the server. You can pick any and give a reason, it's valid. So I think I'm going to go with the switch because it has it's connected to all the computers, right? So since it's connected to all computers, it can share access. The computers can share access of the router. Okay, if you were to say server, then you could say that the server will process the requests. So let me just check the MS for this one. Yeah, the server will process the requests and authorize traffic. So yeah, you can write either one and then give a corresponding reason. I think the switch is much easier. Describe the role and function. So there's 2. There's the role and the function of a router in a network. Okay. So what does a router do? It will basically receive packets of information or whatever. It will receive router. So it will receive packets from either internet or random devices, right? And then it will trace down the IP address on the packet, the destination of the packets, and it would send it out to the destination. Alright, that's basically it. It acts as a gateway. You could say a lot of things about the router, but it simply receives using the IP address. Now this IP address is important to write or you won't get that mark. And then forwards it you can also say it finds the most efficient path to forward it, right? Which means that it will check for traffic and see which way is most efficient in that. So this efficient path is important to write. It can act as a gateway. So I'm just writing everything that comes to mind. Okay, So all of these are points on the MS. So any 3 can get you 3 marks for this one. Alright, looks like we're at the end of this paper. So yeah, do let me know if you understood everything, and if there's any question, feel free to ask me in the comments and I'll reply. Thank you so much for watching. I hope you subscribe and stick around for more papers and just notes in general. So yeah, bye bye.